Happy New Year's, guys. As you already know, 3i Atlas is not leaving, but it's changing the course towards somewhere. Now, 76 days. That's what remains before everything we think we understand about our cosmic isolation might shatter. While most of the world raised glasses to close out 2025, while celebrations echoed through cities and resolutions were made and forgotten, 3i Atlas was already racing through the void at nearly 40 kilometers per second with no sign of slowing, no sign of deviating, no sign of behaving like the natural objects we've been assured it must be. March 16th, 2026 has become a date embedded quietly in calendars across observatories and space agencies worldwide. A countdown that few are discussing publicly, but that many are tracking privately. A moment when something might happen that forces us to confront questions we've been avoiding. 3 details frame everything that follows. 3 pieces of evidence that don't fit the comfortable narrative we've been told about interstellar visitors passing through our solar system. 3 anomalies that, when examined together, create a picture so disturbing that dismissing them requires more mental gymnastics than accepting what they might actually mean. And we need to examine these details now, before the countdown expires, before March 16th arrives, and whatever is going to happen happens whether we're ready to understand it or not. First detail: magnetic particles are falling through Earth's atmosphere. Not occasionally, not randomly, but persistently, continuously, in a pattern that's too organized to be debris from a fragmenting comet tail. These particles are roughly 10 micrometers in diameter, all of them. Not a range of sizes from submicron dust to centimeter chunks like you'd expect from natural fragmentation. Not a power law distribution where small particles vastly outnumber large ones, but a narrow, tightly constrained size distribution centered precisely at 10 microns with minimal variation. Natural fragmentation creates chaos, creates a spectrum of sizes, creates irregular shapes and unpredictable distribution as material breaks apart under stress. What we're detecting instead looks like precision, looks like manufacturing quality control. Looks like each particle was produced to a specification rather than being the random product of ice cracking under thermal stress or tidal forces ripping material away from a comet nucleus. 10 micrometers isn't arbitrary. It's the threshold size where atmospheric physics becomes interesting, where particles are large enough to survive re-entry heating without completely vaporizing, but small enough that atmospheric drag slows them gently rather than causing them to impact violently. Smaller particles get swept away by upper atmospheric winds, dispersed globally, impossible to track or recover. Larger particles hit harder, embedding deep in soil or ocean sediment where collection becomes difficult or impossible. But 10 micrometers? 10 micrometers lands softly, settles through the atmosphere over days or weeks, remains intact, stays functional if there's function to maintain. If you were engineering a particle meant to survive planetary atmospheric entry and remain operational for whatever purpose it serves, 10 micrometers is exactly where you'd set the diameter. It's the engineering sweet spot between survivability and deliverability, and these particles are magnetic. Show alignment with magnetic fields in ways that suggest internal structure. Not just random metallic dust that happens to respond to magnetism, but organized grains that orient themselves, that show preferred directions, that behave as though they have internal components positioned deliberately to interact with electromagnetic environments in specific ways. The composition makes it worse, makes the natural explanation harder to maintain, because spectroscopic analysis of these particles shows they're nearly pure nickel, not nickel-iron alloy like you'd expect from meteoritic material, not the messy mixture of elements that characterizes natural space debris, but refined nickel, processed nickel, nickel with effectively no iron contamination, despite the fact that iron and nickel are nearly always found together in natural settings. This is the second detail that breaks comfortable assumptions. Nature doesn't produce pure nickel in isolation, doesn't separate nickel from iron cleanly. The 2 elements form alloys, are mixed together in predictable ratios, in meteorites, in planetary cores, in any natural context where metals concentrate. Finding pure nickel, finding composition this clean, is signature of processing, of extraction, of deliberate removal of iron from nickel-iron source material through methods that require technology. It's what you'd expect from manufactured component, from industrial production where purity matters and where contamination is controlled, not from a rock that wandered in from interstellar space, not from debris ejected randomly from some forming planetary system light years away. The isotopic ratios add another layer of strangeness because the nickel isn't quite right. The proportions of different nickel isotopes don't match solar system values perfectly, are shifted in ways that suggest either formation in a different stellar environment around a star with different nucleosynthesis history, or isotopic enrichment, which is a process that requires reactors, requires technology, requires deliberate manipulation of nuclear compositions for purposes that natural processes don't achieve. The third detail is what's happening to 3I Atlas itself as it moves outward from the Sun toward Jupiter. Because the object is glowing, is emitting light, but not the warm orange-red you'd expect from a body heated by proximity to our star and radiating that absorbed energy as thermal emission in infrared and visible wavelengths. Instead, it's glowing blue, cold, eerie, a blue luminescence that intensifies even as the object moves farther from the Sun and solar heating decreases. This contradicts thermodynamics as we understand them for passive objects. Cooling curves are predictable, governed by physics that don't bend for mystery. An object heated by solar radiation should glow brighter when closer to the heat source and dimmer as it recedes, should fade from orange to red to infrared to invisibility as distance increases and temperature drops, should follow the Stefan Boltzmann law that relates temperature to radiated power in ways that are quantifiable and deterministic. 3I Atlas doesn't follow this pattern, shows blue emission that strengthens as solar distance increases. Blue light is high energy, short wavelength, the kind of emission you get from very hot plasmas, from electrical arcs, from processes operating at temperatures far exceeding what solar heating can achieve at the distances where Atlas currently is. The implication is unavoidable. The object carries its own energy source, something internal, something that doesn't depend on sunlight, something that can generate enough power to heat material to temperatures that produce visible blue light despite being hundreds of millions of kilometers from the nearest star. And then there's the trajectory, the path this object is following through our solar system, because it entered on a hyperbolic orbit, moving faster than solar escape velocity, carrying enough kinetic energy to pass straight through and never return. That's what we expected. That's what the early observations suggested would happen. Object comes in from interstellar space, swings past the Sun, gets gravitationally deflected slightly, but maintains enough velocity to exit the solar system and continue its journey through the galaxy. Except that's not what's happening. Instead of passing through, instead of following the purely gravitational trajectory that physics predicts for an uncontrolled object, 3I Atlas is bending inward, is altering its path, is changing course with what looks like surgical precision toward Jupiter, as though the largest planet in our neighborhood isn't obstacle to avoid but destination to reach, target to intercept, rendezvous point that the entire trajectory has been optimized to achieve. Rocks don't do this. Passive objects following gravity don't execute course corrections that improve targeting of specific planetary encounters. They follow deterministic paths set by initial conditions and gravitational forces. You can predict where they'll be based solely on position, velocity, and the gravitational influence of the Sun and planets. No surprises, no deviations, just Newtonian mechanics operating with clockwork precision. But 3I Atlas is showing deviations, small but measurable changes in velocity that aren't explained by outgassing, that aren't correlated with solar heating, that align suspiciously well with what you'd need to do to optimize the Jupiter encounter. The thrust vector, when you calculate it from the observed trajectory changes, points almost exactly along the object's direction of travel, aligned with velocity, optimized for maximum efficiency, exactly what you'd expect from a rocket engine firing along the thrust axis, not what you'd expect from random gas jets escaping from a rotating comet nucleus. Before we go further, before we examine what these three details mean when considered together, I need you to do something. Subscribe to this channel right now, hit that notification bell, because what we're about to discuss isn't being covered adequately anywhere else. The implications are too uncomfortable, the timeline too immediate. But March 16th is coming whether we're paying attention or not, and if you want to follow this investigation through to whatever happens at Jupiter, you need to be here. We're going to track every development, every anomaly, every piece of evidence that either confirms or refutes what the data is suggesting. This is real-time investigation with 76 days remaining. Don't miss what comes next. The dust cloud that 3I Atlas left behind as it passed through the inner solar system doesn't behave like debris, doesn't show the characteristics we expect from cometary fragmentation or from material being stripped away by solar wind and radiation pressure. When scientists measured the optical depth of this cloud, when they calculated how much light it absorbs versus transmits, the value came back as exactly 1, not 0.8. Not 1.3, but 1, precisely. Mathematically exact to the limits of measurement precision. Optical depth is a measure of how opaque something is. 0 means complete transparency. Infinity means total opacity. 1 sits at a specific threshold where roughly 63% of incoming light is absorbed and 37% is transmitted. It's the value where you can see through the medium but not clearly, where details are obscured but presence is confirmed, where a veil conceals specifics while making obvious that something is there. And it's the engineering sweet spot for certain applications, for creating screens that hide without completely blocking, for maintaining visibility while preventing detailed observation, for concealment that doesn't look like hiding because there's transparency, but that prevents the kind of resolution that would reveal structure. Achieving optical depth of exactly 1 over an extended volume requires control, requires managing particle size distribution, spatial density, and geometric arrangement such that light absorption and scattering balance precisely. Natural processes don't create exact values, don't produce optical depth that stays locked at 1 across the entire cloud. Natural fragmentation creates variations, regions where density is higher and optical depth exceeds 1, regions where it's lower and transparency increases, random fluctuations, noise, imperfection. What we're measuring shows stability, uniformity, maintenance of a target value that suggests active control rather than passive dispersal. The deployment pattern adds to this interpretation, because cometary tails follow predictable geometry determined by solar wind. Material gets pushed radially outward from the sun, creates elongated structures that trail behind the comet in ways that depend on particle size and radiation pressure. Dust tails curve gently as particles on ballistic trajectories fall behind the faster-moving nucleus. Ion tails point straight back, directly opposite the sun, as ionized gas is pushed by solar wind. The 3I Atlas particle cloud doesn't follow these patterns, doesn't show the expected geometry. Instead, expands roughly spherically, symmetrically, as though material was released with uniform velocity in all directions rather than being passively swept away by external forces. Creating a symmetric distribution requires energy input, requires a mechanism that imparts momentum to particles such that they move outward from the release point with similar speeds regardless of direction. This is what you'd expect from a deliberate deployment, from a system designed to distribute material evenly through a volume of space, from engineering rather than from geology. And the timing is suspicious because the particle release didn't coincide with perihelion, the point of closest approach to the sun, where solar heating peaks and where you'd expect maximum cometary activity if thermal processes were driving the phenomenon. Instead, the particles appeared later, weeks after perihelion, delayed, timed, as though released according to internal schedule rather than as immediate response to external heating, as though whatever system controls the deployment waited for optimal conditions or for specific position in the trajectory before initiating the release. That's behavior that suggests autonomy. That suggests onboard logic making decisions based on mission parameters rather than just responding passively to environmental conditions. If 3I Atlas carries power source, if it operates independently of solar input, then it can execute timed releases, can wait for specific moments, can deploy particles when the trajectory and geometry are right for whatever function those particles serve. And the uniformity of the particle size distribution is the strongest evidence that this is exactly what's happening, because in every sample collected, from high-altitude aircraft over Alaska to balloon-borne collectors over Antarctica, from ground stations in Europe to ships in the Pacific, the particle size distribution peaks sharply at 10 micrometers. Not a broad range, not the power law distribution that natural processes create, but a narrow bell curve, tight, controlled, the kind of size distribution you get from manufacturing process with quality control, where specifications are set and production is monitored and deviations are minimized, where you're making many copies of the same thing rather than fragmenting material randomly and accepting whatever sizes result. This is industrial production. This is batch consistency. This is the signature of technology creating particles to serve specific purpose where size matters and where variation is undesirable. Natural processes don't care about consistency, don't optimize for narrow distributions, don't produce the kind of uniformity we're detecting unless there are selection mechanisms operating, unless something is controlling what gets released and what doesn't. And these particles are reaching Earth, are falling through our atmosphere now, are being collected and analyzed and documented in ways that prove they're real, they're artificial looking, and they're connecting 3I Atlas to our planet in tangible physical way that goes beyond just being an object we observe from distance. This isn't abstract anymore, isn't just telescopic observations of something millions of kilometers away. It's material here, present, available for direct study in laboratories where spectroscopy and microscopy and chemical analysis can examine it in detail. The pure nickel composition is what stops the natural explanation cold, because iron and nickel are chemically similar, are produced together in supernova nucleosynthesis, are found together in meteorites in roughly consistent ratios that reflect the cosmic abundance of these elements. Separating them completely, removing all iron contamination from nickel, requires processing, requires smelting or chemical extraction or some method that exploits the slight differences in their properties to achieve purification. And we can do this. Human industry does this routinely. We extract nickel from ores, refine it to high purity for applications where iron contamination is problematic. It's established technology, but it's technology, not nature. Nature mixes, industry separates. Finding separation this clean in particles that supposedly came from natural interstellar comet is red flag that can't be ignored by claiming we don't understand exotic cometary processes, because this isn't exotic, this is industrial. The isotopic ratios might be even more telling, because nickel exists in several stable isotopes, and the proportions of these isotopes in solar system material reflect the nucleosynthetic history of the elements that formed our sun and planets. Those proportions are known, are measured in meteorites and in solar spectroscopy and in Earth's crust, are consistent enough that deviations are notable. The nickel in the 3I Atlas particles shows deviations, not wild, not impossible to explain through natural variation, but shifted, as though formed in a stellar environment with slightly different neutron flux during supernova nucleosynthesis, or as though processed through nuclear reactions that altered the isotopic mix. Reactors can do this, can change isotopic compositions through neutron capture and decay, can create enrichments or depletions that don't occur in nature. If the particles were manufactured by civilization with nuclear technology, if they're components of systems that operate in nuclear reactors, or that were produced using neutron irradiation, or that have been exposed to radiation environments that shift isotopic ratios, then the deviations make sense, become signatures rather than anomalies, become evidence rather than noise. But all of this, all the particle precision and composition and deployment pattern, exists in context of what 3I Atlas itself is doing, how it's moving, how it's emitting light, how it's maintaining rotation stability that natural tumbling objects don't show. Because the object spins with period of 7.74 hours. Exactly. Measured repeatedly over weeks of observation, no variation detected within the precision limits of the measurements, no drift, no precession, no wobble. This is profoundly unusual for an irregularly shaped object moving through the complex gravitational environment of the inner solar system. Every asteroid we've studied in detail shows some evolution in rotation, speeds up or slows down as tidal forces and radiation pressure create torques. Precesses like a spinning top as gravitational gradients from the Sun and planets act on the non-spherical mass distribution. Shows chaos, shows the fingerprint of natural dynamics operating on body that's responding passively to external forces. 3I Atlas shows none of this. Rotation is locked, stable to within measurement limits, suggesting either impossibly fortuitous combination of shape and density distribution where all the natural torques happen to cancel exactly, which requires coincidence stacked on coincidence or active stabilization. Systems that measure orientation, calculate deviations from desired attitude, fire correction thrusters or spin reaction wheels to counteract perturbations in real time, maintain pointing with precision that serves operational purpose. Instruments need to point, cameras need to be aimed, antennas need to stay aligned with transmitter or receiver targets. If 3I Atlas is probe, if it's carrying sensors or communication systems, then attitude control isn't optional, it's required. The 7.74-hour period might not even be spin in the conventional sense, might be scan rate, the time required for instruments to complete full sweep. The period of a rotating communication beam maintaining contact with multiple ground stations or relay points. And the blue glow becomes even more significant in this context, because if the object is powered, if it has onboard energy source capable of running stabilization systems and deploying particles and potentially operating sensors and transmitters, then waste heat is inevitable. Every energy conversion produces losses. Every system generates heat that has to be radiated, and the temperature at which that heat is radiated determines the wavelength of the emission. Blue light is high-temperature emission, requires surfaces hot enough to glow in the visible blue spectrum. Thousands of degrees, far hotter than solar heating can achieve at the distances where 3I Atlas has been operating. If the blue glow is waste heat from onboard power systems, if it's thermal emission from components running hot because they're converting energy from whatever source the probe uses into useful work, then the intensification as the object moves away from the Sun makes sense. Because the systems might be ramping up, increasing power consumption in preparation for whatever happens at Jupiter, drawing down reserves that have been accumulated over the long journey through interstellar space. Or the blue might not be thermal at all, might be plasma, ionized gas glowing from electrical discharge, the signature of propulsion system that accelerates ions to create thrust, the exhaust from drives that don't use chemical combustion but instead use electromagnetic fields to accelerate charged particles to very high velocities and expel them to generate reaction force. That kind of propulsion produces visible emission, creates blue glow as ions recombine and release energy as light. And it's efficient enough to operate continuously during cruise phases, making small adjustments to trajectory, maintaining course towards specific target. The trajectory is what ties everything together. what converts separate anomalies into coherent picture, because 3I Atlas entered the solar system on hyperbolic path but isn't leaving on one, isn't following the smooth gravitational arc that passive object would trace. Instead shows accelerations, changes in velocity that improve the targeting geometry for Jupiter encounter, that bend the path inward, that create what mission planners would call a trajectory correction maneuver optimized for specific arrival conditions at specific time. March 16th, 2026. That's the date. The moment when 3I Atlas reaches closest approach to Jupiter. Periapsis. The point where distance to Jupiter's cloud tops is minimum and where the object threads through the densest regions of the magnetosphere. And the geometry is precise, the timing surgical, the alignment optimized for something that requires being at exactly the right place at exactly the right time. Jupiter isn't just another planet, isn't just gravitational influence affecting trajectories. It's a dynamo, a generator of magnetic fields that extend millions of kilometers into space. The strongest magnetic environment in the solar system, powered by metallic hydrogen churning deep in the planet's interior and creating fields that trap charged particles and accelerate them to near relativistic velocities and produce radiation belts that would kill unshielded humans in minutes and fry unprotected electronics almost as quickly. For a natural object, for passive comet passing through, this environment is just another hazard. Something that might affect charged particles in the coma or create aurora-like displays through interactions with any gas being released. But for a probe, for technology designed with understanding of what Jupiter represents, the magnetosphere is resource, is tool, is planetary scale amplifier that can boost signals to levels impossible to achieve with onboard transmitters alone. Because electromagnetic signals attenuate with distance, spread out, weaken, follow inverse square law where power density drops as 1 over distance squared. For signals trying to cross interstellar distances, trying to reach targets light years away, this attenuation is brutal. Even high-power transmitters become whispers lost in the background noise of the galaxy after traveling just tiny fractions of interstellar distance. Unless you can couple your transmitter to something larger, unless you can use natural structures as antenna elements, unless you can modulate a planetary magnetosphere and convert it into broadcast station with effective radiated power that dwarfs anything achievable through onboard systems, then the inverse square law still applies, but you're starting from much higher baseline, are amplifying signal at the source by factors that might be thousands or millions, are creating transmission that can cross light years while remaining detectable above background. Jupiter's magnetosphere can do this, can serve as relay, as booster, as the critical infrastructure component that makes interstellar communication practical for probes that don't carry enormous transmitters because they're using planetary resources instead. And the physics is sound, the concept is established. We've studied how to couple electromagnetic signals to magnetospheres, understand how planetary magnetic fields can be modulated, know that the capability exists even if we haven't built hardware to exploit it ourselves because we haven't needed to transmit across interstellar distances yet. But a civilization that sends probes to other stellar systems would need this capability, would need way to report findings, to transmit data collected during the long journey and during the brief passage through the target system, and using the target system's own planets as transmission infrastructure is elegant solution, reduces mass that the probe needs to carry, simplifies design, makes missions feasible that wouldn't be otherwise because you're not trying to cross interstellar distances with signals from small transmitter, but are instead using resources you find at the destination. March 16th isn't arbitrary. It's the date when geometry is optimal, when Jupiter's position relative to potential target stars, relative to the trajectory 3I Atlas is following, relative to Earth and the Sun, all align to maximize transmission efficiency. Miss this window and the alignment degrades. Wait for next orbital period, and you're talking decades or longer. This is one-time opportunity. single chance to use Jupiter for the purpose the trajectory has been optimized to achieve, and 76 days remain. The countdown isn't abstract anymore, isn't just astronomical calculation about when object reaches specific point in its orbit. It's immediate, tangible, evidenced by phenomena we can measure here on Earth right now as the particles continue falling and as the interference patterns become more frequent, and as systems that shouldn't be connected to events happening hundreds of millions of kilometers away show correlations that demand explanation. 76 days might sound like comfortable buffer, like plenty of time to figure out what's actually happening and to prepare for whatever comes next. But when you examine what's already occurring, when you look at the signs that are visible now, you realize that whatever March 16th represents, the process is already underway. The countdown began long before we started paying attention. The silver clouds are the most visible manifestation, the ones that people who aren't watching astronomical data can actually see with their own eyes if they know what to look for and if they happen to be in regions where the displays are occurring. Noctilucent clouds, high-altitude ice formations that typically occur at the edge of space, 80 to 85 kilometers up, where temperatures drop low enough that water vapor can freeze around nucleation particles and create clouds that glow silver blue when illuminated by the sun from below the horizon during twilight hours. These clouds are normally confined to polar regions, are seen in summer months at high latitudes where atmospheric dynamics create the conditions necessary for their formation. They're beautiful, are photographed by enthusiasts, are studied by atmospheric scientists interested in how the upper atmosphere responds to climate change and how human activities might be affecting these remote regions of our planet's envelope. They're exotic but explained, understood, expected in certain places at certain times, except they're not staying in those places anymore. Reports are coming in from mid-latitudes, from regions that shouldn't be seeing noctilucent clouds at all. Central Europe, American Midwest, Northern Africa, observers at latitudes that are far too low, at times of year that are wrong, under atmospheric conditions that don't support the conventional formation mechanism, are photographing displays that look like noctilucent clouds but that shouldn't exist where they're appearing. And when atmospheric scientists analyze the displays, when they measure the altitude and composition and nucleation properties, the anomalies become clear. The clouds are forming at the right altitude, 80 kilometers up, where the cold mesopause creates temperatures low enough for ice formation. But the nucleation particles aren't the usual suspects, aren't meteoric dust or sulfate aerosols from volcanic eruptions or the other natural particles that typically seed high-altitude ice crystal formation. They're the 10-micrometer grains, the magnetic nickel-rich particles from 3I Atlas. Spectroscopic analysis of the cloud composition, sampling done by high-altitude aircraft and balloon-borne collectors, confirms the presence of these particles embedded in the ice crystals, confirms that the anomalous cloud distributions are being caused by the anomalous particle distributions, that the expansion of noctilucent cloud sightings to regions they shouldn't reach is direct result of the particle deployment creating nucleation sites where none should exist naturally. This is proof of concept in the most literal sense, proof that the particles are reaching Earth, are penetrating the atmosphere, are settling at altitudes where they interact with atmospheric water vapor and create visible effects. If these particles are sensors, if they're designed to sample Earth's atmosphere and measure composition and detect conditions, then the clouds mark where they're concentrating, show the geographic distribution of the deployment, make visible the coverage pattern of whatever network is being established. And the pattern is global, is spreading. Started appearing in regions closest to the 3I Atlas trajectory during its passage through the inner solar system and has been expanding outward as particles disperse through atmospheric circulation. The coverage is increasing with time as more particles arrive and as atmospheric transport distributes them to regions they haven't reached yet. By March 16th, if the deployment continues at current rate, the particle concentration might be sufficient to create noctilucent cloud conditions at essentially any latitude under the right atmospheric moisture conditions. That's saturation. That's global coverage. That's achieving the kind of distribution you'd want if you were deploying a sensor network designed to sample the entire planet's atmosphere rather than just monitoring specific regions. And the timing relative to the Jupiter encounter creates a sequence that looks planned. Step 1. Deploy particles during passage through inner solar system. Step 2. Allow particles to disperse and establish coverage. Step 3. Use Jupiter encounter to transmit collected data. Mission architecture that makes sense if the goal is comprehensive atmospheric survey followed by data relay. But the clouds aren't the only visible effect, aren't the only way these particles are making their presence known. The interference patterns are becoming harder to ignore, are showing up in systems that are monitored continuously by operators who notice when performance degrades or when anomalies cluster in ways that suggest correlation rather than random failure. GPS satellite constellations have logged increasing numbers of intermittent anomalies where receivers temporarily lose signal lock, where navigation solutions degrade from meter-level accuracy to kilometer-level or worse, where the normally robust positioning system that we depend on for everything from aircraft navigation to time-stamping financial transactions shows glitches that shouldn't happen absent major disruptions like solar storms or intentional jamming. And there are no solar storms, no geomagnetic disturbances of the magnitude that would explain the GPS degradation, no sunspot activity producing the kind of ionospheric turbulence that interferes with satellite signals. The space weather is quiet, the sun is behaving normally, and yet the GPS anomalies continue. Cluster show temporal patterns that correlate with something other than solar activity. They correlate geographically with regions where noctilucent cloud sightings are most frequent, where particle concentrations are highest, where the 10 micrometer grains are reaching the lower atmosphere in sufficient numbers that their presence might be affecting electromagnetic propagation. If the particles are active, if they're not just passive dust, but are instead components with electromagnetic properties, then their presence in the atmosphere could create interference through mechanisms we don't fully understand because we've never encountered this situation before. Communication satellites show similar problems. Transponders go offline briefly, data packets drop. Error correction protocols work over time, compensating for signal degradation that operators attribute to equipment aging or random failures. But that's clustering in time and geography in ways that random failures don't. The anomalies started appearing after 3I Atlas passed perihelion, have been increasing in frequency as particle concentrations in the atmosphere build, and are most severe in regions where the particle density is highest based on noctilucent cloud observations. This is correlation, not proof of causation, but pattern that demands explanation. That requires either identifying the natural mechanism that creates coincidental timing between interstellar visitor passage and terrestrial communication problems, or accepting that the correlation might be real, that the particles might be causing the interference, that we might be experiencing the side effects of a deployment system testing whether its network is operational. Radio telescopes add another dimension, because they're designed to detect faint signals from astronomical sources, are extraordinarily sensitive to electromagnetic radiation across wide range of frequencies, are monitored by operators who know what natural radio sources look like and who can distinguish between cosmic signals and terrestrial interference, and who notice when something unusual appears in the data, and unusual signals are appearing. Brief transient bursts that don't match known pulsar profiles, don't correspond to any catalogued radio source, don't repeat in ways that would allow triangulation to pinpoint origin, just appear, fade, gone before detailed analysis can characterize them fully. The frequency ranges are specific, not spread across the entire radio spectrum but concentrated in bands that aren't allocated to terrestrial broadcasts. that don't correspond to natural atomic transitions that create spectral lines that look chosen rather than random. Some researchers think these transients are coming from 3I Atlas itself, our short-range communications as the object coordinates with its deployed particle network, our status updates or commands or data exchanges happening at frequencies and power levels that we can detect when conditions are right, but that aren't intended for our observation. We're overhearing rather than being addressed, are catching spillover from communications that serve internal mission purposes. The timing is significant because these signals started appearing after the particle deployment began, after the noctilucent clouds started showing up in anomalous locations, after GPS and satellite systems started experiencing the interference. The sequence suggests activation, suggests that systems that were dormant during the approach phase are now operating, that whatever 3I Atlas is doing, it has moved from passive transit mode to active mission execution mode. And that transition happened on schedule relative to the March 16th encounter date. If you're coordinating a network, if you're deploying sensors or relays or whatever these particles are, and you need to verify they're operational before you commit to the transmission phase of the mission, then you test them, you activate systems, you send status queries, you verify that receivers are responding and that data links are functional, and that the infrastructure you've spent months or years deploying is actually ready to serve its purpose when the critical moment arrives. That's what the radio transients might represent. That's what the GPS interference might indicate. That's what the correlations between particle distribution and communication anomalies might mean. Testing phase. Verification that step 1 of the mission executed successfully. Confirmation that the network is in place and operational. Preparation for step 2, which happens at Jupiter on March 16th when the transmission window opens and when whatever data has been collected gets relayed using the magnetosphere as amplifier. The James Webb Space Telescope situation adds institutional confirmation to what the physical evidence suggests, because Webb, floating at Lagrange point L2, roughly 1.5 million kilometers from Earth, was designed for a 10-year mission, was launched in late 2021 with enough fuel and operational margin to keep observing through the early 2030s, barring catastrophic failure. The mission timeline was set. The observation programs were scheduled years in advance. Major changes required justification, require review, require explanations for why you're redirecting humanity's most capable space telescope from its primary mission. And yet, maintenance has been scheduled for early 2026. Service mission added to launch manifests with minimal public explanation. New instruments listed in payload descriptions without detailed specifications being released. Hardware upgrades for a telescope that's supposed to be operating nominally according to all public statements. The timing is suspicious. Early 2026 means the service mission concludes just before March, just in time for whatever hardware is being installed to be operational when 3I Atlas reaches Jupiter. You don't schedule major telescope maintenance on a whim. Don't add service missions because you feel like it. You do it when something is broken and needs fixing, or when new capability is required that current hardware doesn't provide. Webb isn't broken, is operating better than specification in most regards, which means the service mission is about adding capability, about installing instruments that weren't part of the original design, about preparing the telescope to observe something specific, something like a potential electromagnetic transmission from Jupiter's magnetosphere, something like high-bandwidth data relay using planetary-scale antenna elements, something like signals at frequencies or power levels that current Webb instruments aren't optimized to detect, but that new hardware could capture if it's positioned correctly and if it's looking in the right direction at the right time. The operational details aren't public. The specifications for the new instruments aren't released through normal channels. The justification for the timing isn't provided in the launch manifests or in the mission updates. It's happening quietly, is being implemented without the publicity that major telescope upgrades usually receive, as though someone already knows something is out there. as though observations or intelligence or analysis has identified that March 16th matters. That Jupiter needs to be watched with equipment that wasn't originally planned because the original equipment isn't adequate for what might be detected. Ground-based telescope networks have made similar adjustments, have reallocated observation time, have shifted schedules to focus on Jupiter during the encounter window. Radio telescope arrays that normally spend their time scanning distant galaxies or searching for pulsar signals have added observation programs targeting the outer solar system, targeting Jupiter specifically, waiting, listening, prepared to record whatever happens when 3I Atlas threads through the magnetosphere. SETI programs, normally dedicated to scanning distant star systems for signals from extraterrestrial civilizations, have turned inward, have pointed their dishes at our own planetary neighborhood, at Jupiter, at the region of space where the encounter will occur. The public explanation is that this is just another target, just another potentially interesting observation that fits within the broad SETI mission. But the timing and the coordination suggest something more focused, suggest that the SETI community has recognized that first contact, if it happens, might not come as radio transmission from light years away, but as physical event in our own solar system. This is preparation. This is institutional acknowledgement that March 16th matters, even if that acknowledgement isn't being stated explicitly in public communications. The scheduling changes, the hardware upgrades, the coordination across multiple observatories and programs, all pointing toward the same conclusion. Someone in the space science community has recognized that the 3I Atlas Jupiter encounter might be more than just another astronomical event, might be something that requires watching with full attention and maximum capability. And that recognition is based on data, on analysis of the trajectory anomalies and the particle deployment and the rotation stability and all the features that resist easy natural explanation, on calculations showing that the geometry and timing are precise enough to look planned rather than coincidental, on the accumulating evidence that this object behaves differently than passive interstellar wanderer would behave and that the differences matter. The pattern of previous visitors reinforces this interpretation because 3I Atlas isn't isolated, isn't the only anomalous interstellar object we've detected. It's the third in a sequence that's showing decreasing intervals and increasing strangeness. And sequences imply relationship, imply that these aren't independent random events but are instead connected, part of something larger, iterations of a process that's being refined over time. Oumuamua arrived in October 2017, was the first confirmed interstellar visitor, shocked the astronomical community by existing at all because before Oumuamua we had theories about interstellar objects but no detections, had models predicting they should exist but no proof that the models were right. Oumuamua provided that proof, demonstrated that yes, objects do wander between star systems and yes, our detection capabilities are finally good enough to spot them. But Oumuamua was more than just detection, was anomalous from the start, showed elongated shape unusual for natural objects, tumbled in ways that suggested non-spherical geometry, and then as it retreated from the solar system, it accelerated, showed non-gravitational force adding velocity in ways that couldn't be explained easily through conventional outgassing because no one detected the gas that should have been visible if sublimation was providing the thrust. Researchers proposed solar sail, suggested the object might be flat reflective structure pushed by sunlight. The physics worked. Light carries momentum. Photons pushing on surfaces create force. For thin enough structure with large enough area-to-mass ratio, radiation pressure could account for the observed acceleration. But that required the object to be remarkably thin, thinner than anything natural processes typically create, thin enough that artificial origin became plausible alternative to exotic natural explanation. The proposal was controversial. Still is. Most astronomers prefer to believe that unknown natural processes will eventually explain Oumuamua rather than accepting that it might be artificial. But the hypothesis wasn't dismissed, was published, was debated, remains on the table as possibility that fits observations at least as well as natural alternatives. And the fact that serious researchers at legitimate institutions proposed artificial origin for Oumuamua set precedent, established that the question is acceptable to ask even if the answer makes people uncomfortable. Then, 2I A Borisov arrived in August 2019, less than 2 years after Oumuamua, second confirmed interstellar visitor. This one looked more conventional initially, showed visible coma and tail, exhibited outgassing that spectroscopy could detect and characterize. Seemed like it was going to be the normal interstellar comet that vindicated those who thought Oumuamua was just unusual natural object rather than anything artificial. But Borisov had its own anomalies. Composition was off, enriched in carbon monoxide relative to water compared to typical solar system comets, suggesting formation in colder stellar environment where carbon monoxide ice could condense and be retained. That's explicable. Different star systems have different temperatures and different chemical compositions and would produce comets with different ice ratios. Natural explanation that fits observations. Except the enrichment was extreme, was more dramatic than models of typical stellar environments would predict, suggested either very unusual formation conditions or processing that concentrated carbon monoxide through mechanisms we don't fully understand. And the trajectory showed features that looked optimized in ways that bothered researchers who studied it carefully. Not as dramatic as what we're seeing with 3I Atlas, but subtle enough that those paying attention noted the patterns. 2 visitors in 2 years. First one possibly artificial, second one compositionally unusual, and now 3I Atlas arriving in late 2025, just over 6 years after Borisov, showing anomalies that exceed both previous visitors in number and significance. The intervals are decreasing. First gap was roughly 2 years. Second gap is roughly 6 years, but that's still shorter interval than you'd expect if these were random arrivals following Poisson statistics. Random events don't show decreasing intervals consistently, don't create patterns where visits become more frequent over time unless the detection rate is improving. And while our detection capabilities are improving, they're not improving fast enough to account for the apparent increase in visitor frequency. The surveys are getting better, but not 3-fold better in just 8 years. Something else is driving the pattern. If these objects are part of a network, if they're probes from coordinated mission rather than random debris, then the pattern makes sense, becomes expected rather than coincidental. You don't send one probe to survey a stellar system. You send multiple staggered in time, each building on data collected by previous missions. First probe is reconnaissance, confirms basic parameters, measures stellar properties and planetary positions and orbital characteristics, establishes baseline. Second probe is follow-up, carries instruments refined based on first mission's findings, targets specific questions that first mission identified, looks for features or conditions that baseline survey suggested might be present, validates preliminary conclusions, checks whether things have changed since first visit. Third probe is detailed survey or reporter, has accumulated data from previous missions, knows what's interesting, knows what to focus on, executes targeted observations designed to answer specific questions, and then transmits findings, reports results, uses whatever communication infrastructure is available, like Jupiter's magnetosphere, to relay comprehensive update back to wherever the mission originates. That's the pattern 3I Atlas fits. That's what the decreasing intervals suggest when you interpret them through the lens of coordinated exploration rather than random traffic. And the trajectory clustering supports this interpretation because when researchers back-calculate the incoming vectors, when they determine which direction in the galaxy these objects approached from, the directions aren't randomly scattered across the sky. They cluster, not perfectly. Not all from exactly the same point, but concentrated within relatively narrow cone, within a region that doesn't align obviously with nearby stellar nurseries or galactic structure or any natural feature that would explain why multiple interstellar visitors would happen to approach from similar directions. The clustering could be selection effect. Could be that our detection capabilities are better for objects approaching from certain directions than others. But the bias would need to be strong to create the observed concentration, and there's no obvious reason why detection would be that directionally dependent. Or the clustering is real. Is evidence that these objects do originate from common source, from stellar system or region of space where someone built launch infrastructure and deployed probes on missions that bring them through our neighborhood on trajectories that have similar geometries because they're optimized for similar goals, from civilization that surveyed this region of the galaxy and identified target stars worth investigating and that sent hardware to execute those investigations. If Alpha Centauri is the source, if the nearest stellar system is where these probes launched, then the timing works. Signal from there takes roughly 4 years to reach us at light speed. If Oumuamua transmitted report in 2017, that data would arrive at Alpha Centauri in 2021, would inform decisions about what Borisov should focus on, would shape the mission parameters for follow-up probe launched to arrive at our solar system in 2019. And Borisov's report, transmitted in 2019, would reach Alpha Centauri in 2023, providing input for 3I Atlas's mission planning. That's iterative exploration. That's how you'd run survey program if your patient civilization operating on timescales where years or decades between mission updates is acceptable, where you can afford to wait for light-speed communication because your institutional lifetime exceeds individual human lifespans by factors that make waiting irrelevant, where building knowledge slowly through sequential missions is standard procedure rather than urgent race. But Alpha Centauri might not be the source. The trajectory clustering points slightly away from the nearest stars, toward region where no obvious candidates exist within 10 light years. That could mean the network is more distant, that probes travel farther than we're assuming, that the civilization or civilizations operating this infrastructure are based at stellar systems we haven't identified yet as relevant because we're not thinking about the right distance scales or the right directions. Or it could mean waypoints. Could mean the probes don't come directly from their origin, but instead navigate through network of relay stations or refueling stops or navigation beacons scattered through interstellar space. Could mean the approach directions cluster because there's infrastructure channeling traffic, like ships following established trade routes rather than sailing directly between ports because the routes pass through waypoints that provide services or avoid hazards. That's speculation built on limited data, is extrapolation beyond what the evidence firmly supports. But it's informed speculation, is attempt to make sense of pattern that exists and that requires explanation. That challenges the comfortable assumption that interstellar space is empty except for random debris, and that any visitors we detect are isolated objects with no connection to anything else. The evidence suggests otherwise, suggests organization, suggests relationship between the visitors even if we don't understand the full scope of that relationship yet, suggests that March 16th isn't just moment when one object reaches one planet, but is instead part of larger sequence, part of mission architecture that extends across years and across light years, and that treats our solar system as one target among potentially many in a survey program operating at scales we're only beginning to comprehend. And 76 days remain until the next step in that sequence executes, until 3I Atlas reaches Jupiter and does whatever it's been traveling toward this specific encounter to do. The physics of what happens at Jupiter on March 16th is what converts speculation into testable predictions. What transforms the suggestion that 3I Atlas might be artificial from uncomfortable hypothesis into scenario we can evaluate through observation, because Jupiter's magnetosphere isn't abstract concept, isn't something we're guessing about based on limited data. It's one of the most studied environments in the solar system. We've sent multiple spacecraft through it, have measured its properties extensively, Understand how it operates and what capabilities it provides to anything that can survive the radiation environment and successfully couple to the magnetic field structures. And those capabilities are extraordinary, are exactly what you'd need if you were designing an interstellar communication system and wanted to maximize signal strength while minimizing the mass of hardware your probe needs to carry. The magnetosphere extends millions of kilometers into space, creates a magnetic bubble around Jupiter that's larger than the Sun in terms of the volume it occupies. Within that bubble are trapped charged particles, electrons and ions accelerated to near relativistic velocities by the rotating magnetic field, creating radiation belts that are far more intense than Earth's Van Allen belts, that represent lethal environment for biological organisms and degrading environment for most electronics. Spacecraft passing through Jupiter's magnetosphere require heavy shielding, need protection for sensitive instruments and computers, accept mass penalties to achieve radiation hardness that lets systems survive long enough to complete their missions. Our Juno probe, currently orbiting Jupiter, uses trajectory that minimizes time in the most intense radiation zones, dips in for close passes at the planet, and then retreats to higher altitude where radiation levels are lower, manages exposure to extend mission lifetime. But 3I Atlas isn't minimizing radiation exposure, isn't approaching Jupiter on trajectory that avoids the high radiation regions. Instead, the periapsis, the closest approach point, threads directly through some of the most intense zones, through regions where radiation flux reaches 10 million rads per year, where exposure time measured in hours is sufficient to degrade unshielded electronics to failure, where biological organisms would be sterilized instantly. For natural comet, this trajectory makes no difference. Radiation doesn't affect ice and rock significantly, might alter surface chemistry slightly through sputtering and radiolysis, but doesn't prevent the object from passing through and continuing on its way. The comet doesn't care about radiation because it has no systems to protect, no electronics to shield, no mission to complete. That depends on maintaining functionality through hostile environment. But for a probe, for technology that needs to operate in this environment, the trajectory choice tells you about construction, about capabilities, about shielding technology that exceeds what we've achieved. Because if 3I Atlas is deliberately targeting the high radiation zones, if it's choosing to pass through regions where our hardware would fail, then it's built to handle conditions we can't handle. Built with materials and design approaches that provide radiation hardness beyond our current engineering capability. Or the mission profile accepts that survival beyond the encounter isn't necessary, that the probe's purpose is fulfilled during the Jupiter passage and afterward doesn't matter. That whatever transmission or observation or data collection happens at periapsis is the terminal mission phase, and whether the probe continues functioning afterward is irrelevant to mission success. Designing for one-time use, for hardware that completes its purpose and then becomes debris. Either interpretation suggests sophistication. Either the probe is advanced enough to survive what would destroy our technology, or it's optimized enough to accept limited lifetime in service of mission goals that prioritize data relay over longevity. Both scenarios indicate design, indicate choices made by engineers balancing requirements and constraints and capabilities in ways that natural objects don't, because natural objects don't make choices. The radiation environment is just one aspect. The magnetic field structure is what matters for the communication hypothesis. Because Jupiter's field isn't uniform, isn't simple dipole like Earth's field approximately is. Instead, Jupiter's field is complex, distorted by the rotation of the planet and by the interaction with the solar wind and by internal dynamics in the metallic hydrogen layer that generates the field. Creates structures, field lines that thread through the magnetosphere in complex geometries that couple different regions magnetically, and these field lines can act as waveguides, can channel electromagnetic radiation, can create paths along which signals propagate with less loss than they would experience traveling through free space. If you can inject a signal into the field line structure, If you can modulate the magnetic field locally through interaction with charged particle populations or through direct electromagnetic coupling, you can create disturbances that propagate along field lines and that can be detected at large distances. This is how Jupiter's moon Io creates radio emissions that we detect from Earth. Io orbits deep within Jupiter's magnetosphere. Its volcanic activity releases charged particles that interact with the magnetic field. That interaction creates electromagnetic waves that propagate along field lines and that couple to Jupiter's ionosphere and that ultimately escape the magnetosphere as radio waves we can detect with ground-based telescopes. Io acts as electromagnetic source. Jupiter's magnetosphere acts as amplifier and antenna. The result is radio emissions powerful enough to be detected across interplanetary distances. If Io can do this unintentionally through volcanic activity, then a probe designed to exploit the same physics could do it much more effectively, could position itself optimally relative to the field line structure, could inject electromagnetic signals at frequencies and modulation patterns chosen to maximize coupling efficiency, could convert Jupiter's magnetosphere from passive environment into active transmitter broadcasting whatever data the probe wants to send. The periapsis geometry for 3I Atlas places the object in regions where field line density is high, where magnetic field strength is strong, where coupling between the probe and the magnetosphere would be most effective. The trajectory isn't random passage through Jupiter's vicinity. It's targeted approach to specific location in the magnetic field structure where the physics is most favorable for electromagnetic interaction. And the timing matters because Jupiter's magnetic field rotates with the planet, completes one rotation every 9.9 hours. That rotation creates temporal structure in the magnetosphere, creates windows when specific field lines are aligned favorably for transmission toward specific directions in space. If you want to send signal toward particular target star, toward wherever the probe's home system is located, you need to transmit when the field geometry is right, when the field lines that can carry your signal are pointed in the correct direction. March 16th at 14:33 UTC, that's the predicted periapsis time, the moment when 3I Atlas reaches closest approach to Jupiter, and that time isn't just when distance is minimum, it's when the magnetic field geometry is optimal, when Jupiter's rotation has brought the relevant field structures into alignment, when transmission window opens, when everything that's been planned for potentially years converges into brief period where physics and geometry and mission requirements all align. Miss this window by hours and the field geometry is wrong. The coupling is less efficient. The transmission doesn't reach the target with adequate signal strength. Arrive early or late by days and you're in wrong position relative to the magnetosphere structure. The periapsis occurs in regions where field lines don't support the propagation modes you need. By weeks, and the planetary alignments are off. Earth and Jupiter and target star systems aren't positioned correctly relative to each other. The transmission path is blocked or attenuated by intervening plasma or planetary magnetic fields. This is one-time event, single opportunity that won't repeat on timescales that matter to missions with finite resources. Get it right on March 16th, or the mission fails. That's the pressure. That's the constraint that makes the trajectory precision, and the timing accuracy and the acceleration adjustments all make sense as components of mission designed to achieve specific outcome at specific moment. And if transmission is the purpose, if Jupiter is being used as relay, then the target matters. Who or what is receiving the signal? Where is it located? What information is being transmitted? And why does it matter enough to justify interstellar mission using planetary magnetosphere as transmission infrastructure? Alpha Centauri remains the obvious candidate if we're thinking about nearby stellar systems. 4 light-years away. Close enough that signals reach it within a human lifetime. Far enough that direct transmission from small probe would be challenging without amplification. But if signal is transmitted from Jupiter using the magnetosphere boost, if effective radiated power is increased by factors of thousands or millions through coupling to planetary scale magnetic structures, Then the signal can cross 4 light-years and arrive with enough strength to be detected and decoded by receivers at the destination. The timeline supports this if we're thinking about iterative missions. Oumuamua transmitted in 2017. Signal arrives at Alpha Centauri in 2021. Borisov transmitted in 2019. Signal arrives in 2023. Now 3I Atlas transmits in March 2026. Signal arrives in 2030. Each report updates the mission planners, provides data about current conditions in our solar system, informs decisions about whether follow-up missions are warranted and what they should focus on if they're dispatched. But the trajectory clustering suggests the source might not be Alpha Centauri, points to directions where no obvious stellar candidates exist within 10 light-years. That could mean the network is based farther away than we're assuming, that signals travel decades rather than years, that the civilization or civilizations operating this infrastructure think on timescales where decade-long communication delays are acceptable because their existence spans millennia or longer, or the transmission isn't going to the origin point, isn't report back to home base, is instead communication with other elements of the network, with other probes operating in nearby stellar systems, with relay stations positioned in interstellar space, with infrastructure we don't know about because we're not looking for it and wouldn't recognize it if we saw it because we're expecting communication to look like radio signals between planets rather than like distributed network using natural structures as amplifiers. The content of the transmission is something we can only speculate about unless we successfully intercept and decode it. But we can make informed guesses about what data would be valuable, what information would justify the mission architecture we're inferring, what discoveries would matter enough to report. Earth's atmospheric composition is obvious target because atmospheres tell you about planets, about whether they have active geology creating volcanism and outgassing, about whether they have life-producing biosignature gases like oxygen and methane that shouldn't coexist in equilibrium atmospheres, about technological activity creating industrial pollutants that don't occur naturally. Spectroscopy of Earth's atmosphere from distance reveals all of this, shows oxygen levels indicating photosynthetic biology, shows methane levels indicating either biological or geological sources, shows traces of synthetic compounds indicating industrial civilization. If 3I Atlas has been sampling our atmosphere through its particle network, if those 10 micrometer grains are sensors collecting data about chemical composition and isotopic ratios and trace gas concentrations, then the probe has detailed picture of Earth's atmospheric state as of 2025-2026. Has measurement of pollution levels and greenhouse gas concentrations and evidence of technological civilization actively modifying its planet's atmosphere in ways that are detectable from space. That information matters if you're surveying for life or intelligence, matters if you're tracking how technological civilizations develop and whether they successfully navigate the challenges that come with industrial capability and energy consumption and environmental modification. Matters if you're building database of inhabited worlds and want to know whether this particular example is thriving or struggling or headed towards self-destruction. Electromagnetic signatures are another data category. Because technological civilizations broadcast, produce radio and television signals and radar and communication satellite transmissions that leak into space, create electromagnetic noise that's distinguishable from natural sources. Earth has been radio loud since the mid-20th century, has been producing signals detectable at interstellar distances for decades. Those signals tell you about technology level, about what communication protocols are being used, about what frequencies are occupied, about population distribution if you can map where broadcasts originate. If 3I Atlas has been monitoring our electromagnetic environment, if it's been listening to our broadcasts and our satellite signals and our radar emissions, then it has profile of human technological capability, knows what we've achieved and what we haven't, knows we have satellites and communication networks and radar systems but don't have interstellar propulsion or antimatter reactors or whatever technologies might be common among civilizations older than us, can place us on a developmental timeline, can categorize us as emerging technological species rather than established spacefaring civilization. Orbital infrastructure is visible from distance. Satellites reflect sunlight, create artificial constellation that wasn't there decades ago, shows we're actively using near-Earth space, indicates we've achieved orbit and are maintaining presence beyond our atmosphere. But the scale is modest. Numbers are thousands rather than millions. Sizes are small. Masses are negligible compared to natural bodies. Suggests we're early in space development. Haven't yet built the megastructures that might characterize civilizations that have been spacefaring for longer. All of this data paints picture, creates profile of Earth and humanity as of 2025-2026. And that profile is what gets transmitted if the communication hypothesis is correct, gets compressed into data stream, gets modulated onto the signal that couples to Jupiter's magnetosphere, gets amplified by planetary-scale magnetic structures and broadcast across light years to whatever receivers are positioned to detect it. And we'll be watching. Have positioned ourselves to observe, even though we might not intercept the transmission directly if it's tightly beamed towards specific target rather than broadcasting omnidirectionally. Because even if we don't receive the signal, we can detect that it occurred, can measure the electromagnetic disturbances in Jupiter's magnetosphere, can observe the modulation of field structures and particle populations, can see that something happened even if we can't decode the content. James Webb Space Telescope at L2 will be observing, with whatever new instruments have been installed through the service mission scheduled for early 2026, with capabilities that weren't part of the original mission but that are being added specifically for this event, positioned to watch Jupiter during the encounter window with sensitivities that might detect electromagnetic signatures that would be invisible to other instruments. Ground-based radio telescope networks will be listening, have coordinated observation schedules targeting Jupiter and the surrounding space, are prepared to record across wide range of frequencies looking for anything unusual, for transient signals, for modulation patterns that don't match natural sources, for evidence that transmission occurred even if the signal isn't directed toward us. Spacecraft in the outer solar system might detect something. Juno orbiting Jupiter, New Horizons far beyond in the Kuiper Belt, Voyager probes at the edge of the heliosphere. Any platform that has communication systems and that's monitoring electromagnetic environment might pick up anomalous signals if the transmission is powerful enough and if the geometry allows detection. And then there's the aftermath. The question of what happens after March 16th, after the transmission window closes and 3I Atlas continues on its trajectory outward from Jupiter and deeper into the outer solar system. Does activity cease? Do the particles in our atmosphere become inert? Does the electromagnetic interference stop and the GPS anomalies disappear and the noctilucent clouds return to normal polar distribution? Or does activity intensify? Do the particles activate in response to the transmission? Do they start operating differently than they did during the pre-transmission phase? Do we discover that the deployment wasn't just about atmospheric sampling, but about establishing persistent infrastructure that continues functioning after the probe has moved on? There's also possibility of response if the transmission reaches its target, if receivers at Alpha Centauri or wherever detect and decode the signal, they might respond, might send acknowledgement, might transmit new instructions or queries or information that 3I Atlas or its particle network is designed to receive, and that response would take years to arrive. 4 years minimum if the target is Alpha Centauri, longer if it's farther, creating delay between transmission and reception that exceeds human attention spans, but that might be standard for civilizations operating on slower timescales. Or the network might be designed for one-way communication only, report transmission without expecting response, autonomous missions that collect data and relay it home without requiring acknowledgement or new instructions, operating according to programming that was set before the probe left its origin system, and that doesn't require updates because the mission parameters are simple enough and robust enough to handle whatever situations arise during the survey. We won't know until March 16th. Won't know what actually happens until the encounter occurs and until we can analyze what the observations show. Can't predict with certainty because we're working from limited data and incomplete understanding of what we're actually dealing with. Are forced to build scenarios based on inference and extrapolation rather than on direct knowledge of the probe's design and mission. But the scenarios are constrained by physics, by what's possible given the magnetosphere structure and the trajectory geometry and the observed properties of 3I Atlas. The transmission hypothesis is grounded in real electromagnetic physics, isn't requiring magic or unknown forces, is using capabilities that we understand even if we haven't implemented them ourselves, because we haven't needed to transmit from Jupiter and don't have the technological sophistication to build hardware that could survive the radiation environment. The countdown continues, 76 days becoming 75, becoming fewer as time passes and as March 16th approaches. Each day bringing us closer to the moment when ambiguity might resolve, when the artificial hypothesis might be confirmed or refuted, when we might witness an event that changes everything about how we understand our place in the galaxy. And the signs continue accumulating. The noctilucent clouds spreading, the interference patterns persisting, the radio transients appearing, the institutional preparations proceeding quietly, all pointing toward the same conclusion that something is happening, that March 16th matters, that we're watching a sequence unfold according to plan we didn't write and weren't consulted about, but that we can observe and analyze and attempt to understand before the critical moment arrives. The particles falling through our atmosphere right now are evidence, are physical proof that 3I Atlas touched Earth in tangible way, that whatever this visitor is, it left something behind, deployed something that persists in our environment, and that might continue operating long after the object itself has left the solar system. Those particles can be collected, can be studied in laboratories, can be analyzed with instruments that might reveal structure or composition or functionality that remote observations can't detect. And people are doing this work, are flying high-altitude aircraft to collect samples, are launching balloons to gather atmospheric particles, are using electron microscopes and mass spectrometers and other analytical tools to characterize what these grains actually are, beyond the basic spectroscopy that shows they're nickel-rich and uniform in size. The results of those studies might not be public yet, might be restricted because of national security concerns, or because researchers want to verify findings before publishing, or because someone has decided the information is too sensitive to release. But the work is happening, the particles are being studied, and what's being learned might inform how we interpret the March 16th encounter, might provide context that makes the transmission hypothesis more or less likely, might reveal capabilities or structures that strengthen the artificial explanation, or that identify natural mechanisms we haven't considered. 76 days. The number decreases daily. The countdown is automatic, unstoppable. March 16th will arrive regardless of whether we're ready, regardless of whether we've figured out what we're actually watching, regardless of whether institutions have prepared adequately, or whether the public has been informed, or whether anyone has thought through the implications of what confirmation of artificial origin would mean. And maybe that's appropriate. Maybe we shouldn't be preparing too much, shouldn't be building narratives before we have facts, should just observe and record and analyze and let the data tell us what happened, rather than deciding in advance what we expect or hope or fear to see. Science works best when observations lead, rather than when theories dictate, when we follow evidence wherever it points, rather than forcing it into predetermined conclusions. So we watch, we measure, we document, we build instruments and position them to observe. We coordinate across institutions and disciplines and borders because this matters enough to transcend normal professional boundaries and competitive dynamics. We prepare to the extent we can while acknowledging that we're probably not prepared for what actually happens because we don't know what will actually happen, and in 76 days we'll find out. The immediate future is what makes this urgent. What converts the theoretical discussion about whether 3I Atlas might be artificial into practical question about what we do in the time remaining before March 16th. Because 76 days isn't long, isn't enough time to build major new infrastructure or launch intercept missions, or fundamentally change our observational capabilities beyond what's already being implemented through the telescope service missions and the coordinated observation campaigns. But it might be enough time to prepare, to position resources, to ensure that when the moment arrives, we're recording everything we possibly can with the instruments we have. The noctilucent clouds will continue spreading, will reach maximum geographic extent as the particle deployment approaches global saturation. By mid-March, if current trends continue, we might see these displays at essentially any latitude under appropriate atmospheric moisture conditions. The clouds themselves are harmless, are just ice crystals forming on the 10-micrometer grains in the upper atmosphere. Create beautiful displays during twilight that observers photograph and share and celebrate without understanding what's actually seeding the ice formation. But the spread of the clouds marks the spread of the particles, creates visible map of the deployment coverage, shows us in real time how far the network has extended and where concentrations are highest. And that information matters if we're trying to understand what the particle network is designed to do, because the distribution pattern tells you about function. Random dispersal would create global coverage eventually through atmospheric mixing, but wouldn't show the geographic structure we're observing. The clustering in certain regions, the corridors where particle density is elevated above background. Those patterns might reflect atmospheric circulation. Particles transported preferentially along certain wind streams or jet stream patterns that concentrate them in specific latitude bands or geographic regions. That's natural process that could explain the observed structure without requiring the particles themselves to be active or to be positioning themselves deliberately. Or the patterns might reflect functionality, particles concentrating in regions where they can serve their purposes most effectively, where they can sample atmospheric composition most efficiently, or where they can establish communication links with the parent probe, or where they can interact with Earth's magnetic field or ionosphere in ways that support whatever mission they're executing. Active positioning through mechanisms we don't understand because we're not seeing propulsion or directed motion but are somehow getting non-random distribution anyway. Distinguishing between these possibilities requires detailed analysis of how the particle distribution evolves over time, whether it continues following atmospheric dynamics or whether it shows deviations from what passive tracer particles would do, whether particles move against prevailing winds or concentrate in regions where circulation would disperse them or show any behavior that can't be explained through passive transport. Researchers are tracking this, are using the noctilucent cloud distributions as proxy for particle locations, are building models of how the particles should disperse if they're passive and comparing those models to observations, are looking for anomalies that would indicate active behavior. The analysis is ongoing. Results aren't public yet, but the work is being done and will inform our understanding before March 16th arrives. The satellite interference is what creates operational concerns, because GPS is critical infrastructure, is used for navigation by aircraft and ships and vehicles, is used for timing by financial systems and power grids and communication networks, is embedded so deeply in modern technological civilization that we don't notice it until it fails. And failures, even brief ones, even intermittent anomalies that degrade accuracy without causing complete loss of signal, can cascade through dependent systems in ways that create disruptions far beyond the immediate GPS problem. If the interference intensifies as March 16th approaches, if the particle network becomes more active during the final countdown, we might see more serious degradation, might experience outages that last longer than the brief glitches we've seen so far, might have to implement backup systems or operate under degraded capability until whatever is happening resolves. Aviation authorities are aware, have contingency procedures for GPS failure, have trained pilots to navigate using alternative methods if satellite navigation becomes unreliable. But awareness and preparation aren't the same as immunity. If failures occur at scale, if multiple satellite systems experience simultaneous interference, the backups might not be adequate. might not have capacity to handle all the traffic that would normally rely on GPS, might create situations where delays or diversions or groundings become necessary to maintain safety. The probability of this happening is unclear, depends on whether the interference continues at current levels or escalates, depends on whether it remains intermittent or becomes continuous, depends on factors we can't predict because we don't know what's causing it or how it might evolve. Communication satellites face similar risks. Most modern communication infrastructure is redundant, has multiple pathways for signals to reach their destinations, can route around failures without users noticing disruptions in most cases. But redundancy has limits. If enough nodes fail simultaneously, if interference affects broad enough range of satellites, the routing alternatives might exhaust, might create bottlenecks or blackouts in regional or global communication networks. Again, this is possibility rather than prediction. Is scenario we should be aware of rather than outcome we can forecast with confidence. But the increasing frequency of anomalies over the past weeks suggests the situation is evolving, suggests that whatever is happening isn't static but is ramping up towards some culmination that might coincide with the March 16th Jupiter encounter. The radio signals remain enigmatic, the transient bursts that appear and disappear before detailed analysis can characterize them, the frequency patterns that don't match known sources, the timing correlations with other anomalies. If these signals are communication between 3I Atlas and its particle network, they might intensify as the encounter approaches, might increase in frequency or power or duration as the probe coordinates with its deployed assets in preparation for transmission. Radio telescope operators are watching for this, are recording continuously across wide frequency ranges, are using automated detection algorithms to flag unusual signals in real time so that human analysts can examine them while they're occurring rather than discovering them only afterward in archived data. The hope is that if transmission occurs at Jupiter, if the magnetosphere is used as amplifier, we might detect precursor activity, might see the probe testing the communication link, might observe the signals that coordinate the timing and verify that systems are ready. But there's also possibility that we detect nothing, that whatever communication is occurring happens at frequencies or power levels or modulation schemes that our instruments aren't configured to detect, that we're listening in the wrong bands or looking for the wrong signatures, that the technology is sophisticated enough to avoid detection by observers like us who might be monitoring but who aren't the intended recipients. Stealth is possibility that makes everyone uncomfortable. Because if 3I Atlas is designed to avoid detection, if it's operating covertly except for the traces we've managed to observe through careful analysis, then the absence of obvious signals doesn't mean nothing is happening. Might just mean we're not seeing it. Might mean the mission architecture includes operational security measures that prevent primitive civilizations like ours from intercepting communications that aren't intended for us. That would explain the ambiguity, would explain why we're seeing enough anomalies to know something is happening but not enough clear evidence to prove what that something is, would suggest that we're on the edge of the observable, that we've developed just barely enough capability to detect that the probe exists and that it's doing things but not enough to fully characterize what those things are or to intercept the communications or to interfere with the mission. And maybe that's intentional, maybe we're meant to be almost but not quite aware. Maybe the mission architecture includes mechanisms that leave traces for civilizations that have reached certain technological thresholds while remaining invisible to those who haven't. Maybe detection requires developing capabilities that serve as filter, that ensure only civilizations with sufficient sophistication encounter evidence of the network. That would explain the 10 micrometer particles. That would explain the choice of size that's large enough to survive atmospheric entry, but small enough to require advanced analytical techniques to characterize. That would explain the optical depth of exactly one creating visibility without complete transparency. That would explain the pure nickel composition that's anomalous enough to be noticeable to civilizations with spectroscopy and materials science, but not so exotic that it screams artificial to casual observation. Each feature creates threshold, requires developing specific capability to detect the anomaly. Atmospheric sampling at high altitude, spectroscopic analysis, isotopic ratio measurement, electromagnetic monitoring, infrared observation, magnetic field sensing, the full suite of techniques that we've only recently developed and that earlier versions of human civilization wouldn't have possessed. Maybe we're meant to find this now, in 2025, 2026. Because now is when we're capable of recognizing it as anomalous, even if we can't fully understand it yet. The institutional response tells its own story, because the James Webb Service mission and the telescope scheduling changes and the coordination across observatories all happened without major public announcements, without press releases explaining why suddenly everyone is pointing instruments at Jupiter during the same narrow time window in mid-March. The astronomical community has collectively decided that this event matters enough to justify the resource allocation and the coordination effort. But that decision was made quietly, which suggests either that the people making these decisions aren't certain enough to make public claims about what they suspect, or that they are certain but have been advised not to discuss it publicly. Either interpretation is concerning. Either we're preparing for something we think might be artificial encounter, but we're not confident enough to say so, or we're confident but we're being prevented from communicating that confidence to the broader public that might have stake in how we respond to confirmed presence of extraterrestrial intelligence. The policy questions haven't been addressed publicly. If March 16th confirms artificial origin, if we document transmission that can't be explained through any natural mechanism, if the evidence becomes undeniable, what happens next? Who makes decisions about whether to respond, about whether to attempt communication or maintain silence, about whether to treat this as scientific discovery that gets published and discussed openly, or as security matter that requires classification and control? These questions don't have clear answers because we've never been in this situation before. Have protocols for detecting radio signals from distant civilizations through SETI programs. Have discussed for decades what we'd do if we received message from the stars. But physical visitor is different, changes the dynamics, creates immediate proximity rather than vast distance, creates tangible presence rather than abstract signal, and we haven't prepared for this scenario as thoroughly as we probably should have. Different nations might respond differently, might have different priorities about whether contact is desirable or threatening, might have different capabilities to observe or interact or analyze, might compete rather than cooperate depending on how the discovery is framed and what opportunities or risks it presents. The international coordination that's happening now in the observational preparation might not survive the transition to post-confirmation environment where strategic considerations and national interests create pressures towards secrecy or unilateral action. The scientific community generally favors openness, favors publication and peer review and public discussion, believes that discoveries belong to humanity rather than to specific institutions or governments. But scientists don't control policy, don't make final decisions about classification or public disclosure when security or strategic concerns are raised. And artificial interstellar probe is exactly the kind of discovery that would trigger those concerns. That would activate national security apparatus regardless of whether the threat is real, because the uncertainty alone is sufficient to justify treating it as potential security matter. So we might not learn everything, might not get full public disclosure of what's observed on March 16th, might see partial information released while other data remains classified, might experience the frustrating situation where those with access to the best observations and analysis can't share what they've learned, while the rest of us are left speculating based on incomplete public record. Or the evidence might be so clear, so undeniable, so widely observed by distributed network of telescopes and spacecraft and monitoring systems that suppression becomes impossible, that so many independent observers capture the transmission or the magnetosphere modulation or whatever happens, that no single authority can control the narrative, that the discovery becomes public through the sheer volume of data from sources that aren't subject to centralized control. The amateur astronomical community might play a crucial role here, because while professional observatories can be directed to embargo findings and while spacecraft data can be classified, backyard observers operating their own equipment can publish what they see without requiring approval, can share images and measurements through social media and forums and websites that reach global audience instantly, can create distributed verification that prevents any single narrative from dominating. And the amateur community is mobilizing, is aware that something interesting is happening even if the full scope isn't public knowledge, is pointing telescopes at Jupiter, is coordinating observation schedules, is preparing to record whatever happens on March 16th from multiple independent locations using equipment that might not match professional capability, but that's adequate to detect major electromagnetic events or unusual magnetosphere behavior. That distributed observation network is insurance against information control, is guarantee that multiple perspectives will capture whatever occurs and that those perspectives will be shared regardless of what official sources choose to disclose, and that's valuable. Is democratic approach to discovery where the data belongs to everyone rather than being gated by institutions that might have interests in managing how information is released. The 76-day countdown is public information now, not because authorities have announced it, but because enough researchers have noticed the patterns and shared their observations and connected the pieces that the date has entered the collective awareness of people paying attention. March 16, 2026 at 14:33 UTC periapsis, the moment when 3I Atlas reaches closest approach to Jupiter, the moment when everything might converge. People are planning around this date, are scheduling time to watch, are organizing viewing parties or observation campaigns or just marking calendars to pay attention when the time comes, are treating it like eclipse or meteor shower or other predictable astronomical event that's worth witnessing, except this one comes with uncertainty, with the possibility that nothing observable happens, that the encounter is gravitationally interesting but electromagnetically silent, that we watch and record and analyze and conclude that no, there was no transmission, the object is probably natural after all, and we move on having learned that our hopes or fears about artificial origin were premature. That would be disappointing, but not devastating. Would mean we need better explanations for the anomalies, but that natural processes are adequate and that the patterns we thought we saw were either coincidences or misinterpretations. Would mean we remain alone as far as we know, remain uncertain about whether intelligence exists beyond Earth, remain waiting for clearer evidence that might come from future visitors or might never come at all. But if something does happen, if we detect transmission or observe magnetosphere modulation that can't be explained naturally, if March 16th delivers confirmation rather than ambiguity, then everything changes in ways we can't fully anticipate. Because confirmation of artificial origin for 3I Atlas implies confirmation that we're not alone, that intelligence exists beyond Earth, that technological civilization has developed elsewhere and has capabilities we don't possess, and has been operating in our cosmic neighborhood potentially for longer than we've existed as species. The philosophical implications are profound, reshape how we think about humanity's significance, about whether we're unique or commonplace, about whether intelligence is rare gift or inevitable outcome of cosmic evolution, about whether the galaxy is empty wilderness waiting for us to explore or populated neighborhood where we're newcomers joining an existing community. Religious implications vary depending on tradition, but are significant across most frameworks. requires reconciling beliefs about creation and purpose and divine attention with reality that includes other intelligent minds that might have their own relationships with whatever ultimate reality or deity or cosmic principle different traditions recognize. Some theological frameworks accommodate this easily, others struggle. All would need to engage seriously with the confirmation rather than dismissing it or ignoring its implications. Political implications might be more immediate. Because if we're not alone, if there are other civilizations with greater capabilities than ours, then our assumptions about sovereignty and security and independence all require examination. Do we have rights that others might respect or ignore? Do we have protection if someone decides our planet or our resources or our biosphere is valuable and worth taking? Do we have any leverage in potential interactions with civilizations that might be millions of years older and correspondingly more advanced? These are uncomfortable questions that we've mostly avoided by assuming we're alone or by treating the possibility of contact as so remote that planning for it seems unnecessary. But physical visitor in our solar system executing mission that might include transmission from Jupiter makes the questions immediate. Makes planning necessary, even if it's planning for scenarios we can't fully anticipate because we don't know what contact would actually look like or what responses might be available to us. The optimistic interpretation is that if a network exists, if probes are surveying the galaxy and reporting findings, then the builders of that network are interested in knowledge rather than conquest, are exploring because exploration matters to them, are observing rather than interfering, are leaving us to develop according to our own paths without imposing their presence or their values or their technologies on us until we're ready for contact on more equal terms. That interpretation fits what we're observing. Fits the apparent reconnaissance mission architecture where probes pass through and gather data without making obvious contact or altering the systems they're studying. Fits the pattern where we're detecting the network only because our capabilities have reached thresholds that allow recognition even though the network isn't announcing itself or seeking attention. Suggests that we're being given time, being allowed to mature, being monitored but not controlled. The pessimistic interpretation is darker, is that we're being evaluated, that our development is being tracked to determine whether we represent opportunity or threat, that decisions about how to interact with us or whether to interact at all are being made based on criteria we don't understand by entities we've never encountered, that our fate might be determined by remote analysis transmitted from Jupiter to civilization light years away, that makes choices about Earth's future without our input or consent. That interpretation also fits the observations, fits the reconnaissance architecture just as well as the optimistic version does, differs only in assumptions about intent and values and what decisions might follow from the data being collected, and we have no way to determine which interpretation is correct without more information than we currently possess. Without understanding not just that the network exists, but what purposes it serves and what ethics or strategic considerations guide how it operates. So we watch, we prepare, we wait for March 16th to arrive and for whatever happens to reveal more about what we're actually dealing with. We continue the countdown knowing that 76 days is becoming 75, becoming fewer, becoming 0 on a schedule that's indifferent to whether we're ready. And we accept that the outcome might be ambiguous, might not provide the clear answers we want, might leave us still uncertain, but with more data to analyze and more patterns to recognize and more questions to ask. The particles will continue falling, the interference will persist or intensify. The noctilucent clouds will spread farther as global saturation approaches. The preparations will continue with telescopes and spacecraft and monitoring systems all positioning themselves to observe. The coordination will proceed across institutions and nations and disciplines, and the countdown will tick forward inexorably toward the moment when 3I Atlas reaches Jupiter and when we find out whether our solar system has been visited by intelligence that's been watching us for reasons we're only beginning to understand. If you've followed this investigation to this point, if you've engaged with the evidence and the reasoning and the implications, make sure you're subscribed to this channel. Make sure notifications are enabled, because we will be here on March 16th. We'll be covering the encounter live as observations come in. We'll be analysing the data as it becomes available. We'll be reporting what we learn without waiting for official sources to decide what they want to share. This is too important to leave to controlled narratives. Too significant to trust that institutions will provide full transparency. Too immediate to wait for papers to be published months or years after the event. We're going to document this in real time. We're going to share what we observe and what others observe and what can be concluded from the combined observations. We're going to participate in the discovery rather than just waiting to be told what was discovered. 76 days remain. The countdown continues. March 16th approaches whether we're ready or not. And whatever happens at Jupiter on that date, whenever 3I Atlas threads through the magnetosphere at the exact time and location that the trajectory has been optimized to achieve, we'll be watching, we'll be recording. We'll be here reporting to you what we see and what it means and what questions it raises for humanity's future in a cosmos that might be far less empty than we believed. The visitor came from beyond, deployed its network, maintained its course, and now races toward Jupiter carrying data or intent or programming that has guided it across light years and through our solar system toward a moment that was planned before we knew it was approaching. A moment that's coming. A moment that might matter more than anything else happening in human civilization right now, because it might be the moment when we learn we're not alone. 76 days. Mark your calendars. Prepare to watch, because on March 16th, 2026 at 14:33 UTC, we might witness something that changes everything, or we might witness nothing. And either way, we'll know more than we do now about what we're actually sharing this galaxy with. The countdown has begun. The evidence accumulates, the questions multiply, and the only certainty is that March 16th will arrive, and that whatever truth the data has been hinting at will become clearer when the moment finally comes. Stay curious, keep watching, and remember, the universe is under no obligation to make sense to us, but we're obligated to pay attention when it offers us glimpses of its deeper reality. This is one of those glimpses. Don't miss it.